So you can give this children's state graduating ceremony.
Who knows at this point? Okay.
And L, actually, all four.
Alright, you guys have it? Okay. This is forward next, right? Yeah. All right, and if I see me through the foil here, but, all right, we have group 6 up next. Take it away, guys.
Alright, hi guys, my name is Nuo.
I'm Fahim.
I'm Natalie.
And I'm Sam, and we're team AquaROVER. So today we're going to be talking about our problem statement, what we started out with, some basics of sailing, how we designed each of our sailboat components and got them to work, and then final remarks and acknowledgements. So our problem statement was given to us by NASA and Wayne Racer, which is an educational organization. It is to create a vehicle that gathers water quality information like pH, salinity, and conductivity, while also fostering STEM education for underprivileged K-12 students. And so that is a pretty lofty goal. So we defined the objectives for ourselves to be designing and building a fully functioning sailboat while incorporating some type of autonomous system. And that system would be just some predefined route that our sailboat will move in order to collect that water information. And our overall goal for our time with this project was to build a foundational platform for future teams to easily iterate off of. And so, on that note, this is last year's team's design, and they were able to create a remote controlled boat that used a pump and propeller to move through the water. And so our aims and iterations off of this design is to have our sailboat be entirely propelled through the wind alone, improve the maneuverability, especially looking at the rudder and elevator mechanisms, reduce the weight. And you can see here, especially in the sail, which was 3D printed last year, by choosing a different lightweight material that we have there, as well as enhancing the overall aesthetics, and incorporating that autonomous system I talked about before. And so the way we were able to do this was through a lot of professor consultations to learn, how do we even design a sailboat, interviews with the BU sailing team in order to get an intuition on how to sail, and then regular meetings with our customers to make sure that they were satisfied with our overall progress.
So in order to understand the basics of sailing, we first have to start with the basic parts of a sailboat. These include the sail, the keel, and the rudder, and these are parts that we have to implement into AquaROVER. So as you can see in the top right corner there, the keel is very important in ensuring the boat moves forward in the forward direction. And as you can see, the keel opposes or counteracts the forces in the lateral direction of the mainsail and resulting in a net force in the forward direction. And then we also have to talk about a very important parameter in sailing, which is called the point of sail. And this is the direction that the wind comes from with respect to the boat. And as you can see, the most efficient point of sail is when the wind is perpendicular to the boat, traditionally called the beam bridge, as this ensures the maximum lift and the least amount of drag on the sailboat.
So AquaROVER moves very similar to traditional boat with some modified components to it. Originally, when the elevator in the back is at the same angle to the mainsail, the entire structure points towards the wind, just like how a wind vane would work. But as soon as we turn the angle of the elevator in the back slightly, that creates a moment on the entire mainsail and rotates it at an angle of attack with respect to the wind. And this angle of attack is what produces our lift on the mainsail. And at the same time, the keel underneath the boat counteracts with the lateral forces of the lift, resulting in net forward motion. So that's how AquaROVER works. So in order to be more efficient, we have completely redesigned our sail, which is this rigid sail design is much easier to control and automate because the entire structure is controlled just using one single servo motor in the back. The sail is also an airfoil shape, so it works very similar to how an airplane wing would work. The elevator and the sail is fabricated using MDF wood in a laser cutter, and it's stacked up on top of each other and wrapped with a plastic shrink wrap called Ultra Coat to get the airfoil profile to it. And lastly, the nose cone in the front, it's a counterweight which provides stability against pitching. So it's a very important part of our structure of the sail.
Before we started building any of the parts of our sailboat, we carried out some analysis to determine that it was gonna be an effective design. So we used an aerodynamic simulation tool called XFLR for our keel, mainsail, and elevator in order to determine the correct sizing as well as the airflow type to be used for this. The simulation gave us a maximal theoretical lift of 4.6 newtons of force for the mainsail at an angle of attack of 11 degrees, as you can see in the plot on the right, with the given parameters. Therefore, our design was based on theory and simulation that gave us enough confidence that our design was gonna be successful. And also, we got very important information that we would later need for the controls aspect as well as the automation aspect of the project.
Moving on to the keel is essential for stability in our sailboat, and it provides stability in two ways. It provides gravity controlled stability, which prevents the rolling or capsizing action, and form control stability, which prevents skidding of it. So gravity controlled stability comes from the ballast in our keel, which is additional weight that has been added to the internal volume of our keel. And an ideal ballast should be anywhere between 25 to 50% of our boat's total weight. And for us, we chose 30% of the total weight, as this is within the ideal range, but also low enough to align with our weight reduction goals. The way the ballast in the keel works is that when there's a pressure applied by the wind, it causes the boat to tip over due to the heeling moment. And the ballast works to counteract this by producing a righting moment to correct and stabilize the boat. As for form control stability allows our boat to cut through the water, and we get our form control stability from the airfoil of our keel, which is a NACA 0012 airfoil, which produces a lift of 13.5 newtons, and as explained before, this counteracts the lateral forces of the sail to propel our boat forward. As for the rest of the underbody of our sailboat also consists of a rudder which helps control the direction of the boat by changing the flow of the motion of water on the side of the boat. It has an aspect ratio of 2, which refers to the length of the width of the rudder, and this high aspect ratio works well for us as it reduces the induced drag. Along with this, we also opted for a pump for emergency retrieval purposes, as well as to be switched on during the autonomous mode, which Noah will explain later. And we specifically chose a jet propulsion pump rather than a propeller-based pump to reduce drag as well.
Yeah, so now that we've talked about the physical parts of the project, we're gonna go over the electronics portion. And for the controls aspect, we're using this RC controller with the 2 analog sticks mapped to different servos on the boat itself. So by moving the left analog stick left and right, it'll move the rudder. And by pushing it up, it'll turn on the pump, as you can see here. And by moving this stick left and right, it'll change the elevator servo position. And this switch on the top left here is used to switch from manual to the autonomous mode. And so this is just the input and output diagram of our electronics. We are using a Arduino Mega for our microcontroller. And like I said before, the RC controller is used as an input, which the Arduino processes the data and sends the output to the 3 servos for the elevator, the rudder, and then the pump, all of which are powered by a 7.2 volt battery. And the pump is actually also controlled by an ESC so that the voltage that goes into the pump can also be regulated. And in addition to this, for the autonomous portion of our project, we've included 3 sensors: the magnetometer, which will tell us the heading of the boat or what direction the boat is facing, a wind vane sensor to tell us where the wind is coming from, and also an anemometer to tell us the wind speed of the boat, all of which are very important for our autonomous systems.
So as you learned, AquaROVER can be controlled manually using the RC controller. So we took it out into the Charles River one day to do a manual preliminary test, and we were very happy with the results and the outcome of it. The first video shows AquaROVER actually propelling forward just using wind. So it is propelling at a beam reach angle, which means the wind is coming perpendicular while it's propelling forward. So we were confident that the sail actually works as a propulsion system. The second video shows the efficiency of the rudder and how precise of a control we have of the heading of the boat by controlling it manually. Even though the test was successful, we learned about lots of design iterations that were needed. One of them being the elevator sizing. We believed that we needed a bigger elevator to catch or to turn the sail at an angle when there is like less wind. So we designed it to be about like twice as what it was originally. We also added more ballast in the keel, so that will provide more stability against sudden wind in the middle of the river. It also gave us a sense of our operating condition for our boat. We believe that wind speed under 24 miles per hour would be like ideal for our boat. And this test was also very important to get us an intuition of how we would be programming it for the autonomous system.
So yeah, like Raheem said, after we conducted the manual controls test, we then worked on the automation side of things. And our goal for the automation path is basically just to move in a square box-like pattern. And so we thought of it in like two separate steps. The first step is to set the elevator so that it catches the most amount of wind and create the most amount of lift as possible. And this is done with the wind speed and wind direction sensors. So from the wind direction sensor, we calculate the point of sail that Lorenzo talked about earlier. So basically, where the wind is coming from in relation to the hull of the boat. And for each point of sail, we've created a corresponding change to the elevator that will allow us to capture the most amount of lift possible from the wind. And also from the wind speed sensor, we're comparing that against a threshold that we've set manually ourselves in the Arduino. And so essentially what this part does is that if the wind speed is below a certain threshold, we'll turn on the auxiliary pump since there isn't enough wind to move the boat forward at a reasonable speed. And all of this loops with changes in the sensor inputs. And so that's the first part of the automation. The second part is just to move the boat in a square-like pattern. And this is done by using the magnetometer or the heading sensor that we've integrated. And how this works is that we've initially set a target heading to be 0 degrees. And the Arduino will then compare our actual heading versus the target heading and change the rudder accordingly using PID controls. After which the boat is allowed to move forward for 20 seconds. After which the target heading will then be incremented by 90 degrees so that it turns 90 degrees to the right. And this will repeat itself going back to 0 degrees. And again, this also loops with changes to the heading. So the rudder change is dynamic with the changes to the heading inputs. And so for our testing, we've conducted a dry test first, and you can see Lorenzo here using a box fan as our wind source. And it shows promising results with the elevator changing to the position that we want it to, and the mainsail being set at an angle for maximum lift. And the sad news is that once we put it onto the Charles River a second time, for our wet test, our elevator movement didn't work quite as expected, and this is mostly due to the unpredictable natures of winds on the Charles River. There are a lot of oscillatory winds on the river, so basically the wind will come from this direction and then suddenly change to the opposite direction. And that's just something that our wind direction sensor isn't capable of capturing. And there are also like wave motions of the Charles River that will disturb the accuracy of our wind direction sensor, which does not work in our favor. However, the rudder movement does work properly as it moves 90 degrees, as you can see here, after a set amount of time. And for our recommendation to the next team, we recommend using additional sensors such as a magnetometer on the mainsail itself so that we can get the heading or the direction of where the mainsail is in relation to the boat at all times.
Okay, so for final remarks, as I talked about before, our overall objectives for our project was to build or design and build a fully functioning sailboat while incorporating some type of autonomous system. And we believe that we've achieved these objectives by not only having a sailboat that uses wind to move forward, but having that movement be controlled through the use of our updated rudder and elevator mechanisms and stable through our incorporation of our keel and counterweight. We were also able, as Noah just described, to build a working autonomous framework, but the job's not done. There are still things to do, but we believe that we are able to create a solid foundation for future teams to easily incorporate our NASA and RACA goals of water data collection and education curriculum integration. We also hope that future teams will be able to iterate off of our autonomous framework to build a more resilient autonomous system that can operate in varying site conditions.
Finally, we would like to thank our customers, Jeff, Lisa, and Professor Farney, and our advisor, Professor Lin, for being great mentors and guides throughout this project. And also our professors here at BU, the staff at EPIC and the BU sailing team for giving us important and crucial knowledge for bringing this project to fruition.
Thank you.
I'm a control person, I like to control that. For the PID controller that you did you just tune by hand your gates, or did you do some analysis of the dynamics of the system, help inform the controller design?
So when testing the PID portion, it was hard to test it on land because the settings that we would be using it is very different. How the boat would move in the water is very different to how we can move the magnetometer itself. So we were kind of just playing around with the different parameters of the PID controls until we got something that was like the right fit for us. But that required like water testing.
Can you explain a little bit more what the counterweight does for you?
So the counterweight weighs equally as our elevator. So that provides a balanced weight on either direction of the sail. So when it turns, it doesn't have a backward force because of excess weight in the back. And it's machined out of aluminum to get an aerodynamic profile as well.
Yes, that was definitely something we saw in the previous team's design. When their elevator in the back would move, it'd be so heavy that the entire sailboat would continue to move. And that's why we also incorporated a manual stop, which is that wire hanging out the bottom of the sail.
You had mentioned one of your priorities was weight reduction. Because what did you achieve?
So compared to last year's sail design, our sail is almost twice as big in size while being almost significantly, well, like less than half of their weight. That's because it's almost hollow. We are using very light wood and a plastic wrap to achieve the shape of it. And at the same time, we wanted to keep the major weight of it, or the center of gravity, lower towards the hull of the boat. And we achieved that by having less weight on top, but adding more ballast or weight inside the keel.
So was the goal just the sail or the entire?
So our bodyboard can have like about 64 kilograms of buoyancy in it. So we were confident that it was gonna float. It was more about reducing the drag of it when it goes around in the water. So traditionally, we just wanted to reduce the weight of the sail while keeping the center of gravity as low as possible.
We were also able to lower the weight of our rudder mechanism in the back as well by doing a little bit better with our 3D printed design and shrinking the rudder. I don't know if we can show the previous design, but yeah. So this was all 3D printed here, their sail and their elevator mechanism, as well as that gear configuration. We were able to get that down to just one 3D printed part, that little blue, and that servo motor in the back. The elevator also changed as well. It's no longer 3D printed. That rudder mechanism is no longer so protruded out and having all this extra 3D printed parts. And I think that was all the other designs that we did for reducing the weight.
So in the end, when you put it on a scale, how much less?
I don't think we have that.
Yeah.
So the electronics housing has a silicone sealant on the inside, and at one point when we were testing, the boat did tip over, and we were happy to know that none of the electronics were damaged. So the housing does work really well.
So we custom made the housing for our own needs. And then the way the box works is a height tolerance with each of the sides. And then at the same time, we also added aquarium sealant inside to prevent water from going in. And we did test it in water, and it does prevent it from going inside, and we were happy with it.
And there's multiple layers to it. So it's lifted from the hull a little bit, and then the electronics are also lifted inside the electronics box.
So there's 2 layers of acrylic that stop it, the water from coming in as well.
That's the vehicle that was to have it better than the other sailboat last year. So did you achieve that? Regardless of not knowing your total weight of theirs?
Yeah, I mean, we did get wind propulsion as was shown in the test that Kareem showed. So it did propel forward with the sail.
Yeah, I feel like the propulsion not only depends on the weight, but also how much drag is under the water. We reduce that by totally getting rid of an entire motor with a propeller underneath and replacing it with our jet. So that jet also has a significantly less reduced drag under the water. So that helped us with achieving our propulsion goals.
All right, guys.
You know, speak for yourself, right?
All right, guys, thank you very much. Excellent presentation. I think like you out here.